Welcome back to the Deep Dive. Today, we are strapping in for something that feels a bit like a time travel movie, but one where the special effects are just, well, rocks.
Massive continent-sized rocks.
Exactly.
Yeah.
I mean, usually when we talk history, we're talking about, empires, wars, maybe the last few thousand years of human drama.
Sure.
But today, we are rewinding the clock. Way, way back. We're talking about a car crash.
That is certainly one way to frame it.
But it's not just any car crash. I want you to imagine a vehicle the size of a continent speeding north across a prehistoric ocean.
Okay.
And then it just slams into another continent with such force that it crumples the Earth itself, pushes the seabed into the sky. And, I mean, it basically creates the world we see around us today.
It is quite the visual. And you're referring, of course, to the collision of the Indian plate with Eurasia.
That's the one.
It is, without any exaggeration, the defining moment of our geography. It's the event that built the stage we all act on.
Precisely. So today, we are unpacking the structure and physiography of India. And before we get into the nitty-gritty of, tectonic plates and river valleys, I have to give a massive shout-out.
Absolutely.
The team that helped us put this incredible stack of research together, this whole deep dive is very heavily focused on the full summary for UPSC, put out by the Simplified UPSC by PPP YouTube channel.
They've done a truly stellar job. I mean, what they've managed to do is link the standard NCERT textbook material,
Which is India, Physical Environment, Chapter 2.
that and the fundamentals of physical geography, but they link it with actual previous year questions, or PYQs, from the civil services exam.
And that's the magic right there.
Yeah.
It bridges that gap between, just reading the theory and seeing how it's actually tested.
It's the application. It's a goldmine.
It really is. So here's a humble request from us. If you find this deep dive helpful, please go subscribe to the Simplified UPSC by PPP channel. It's incredible work.
It is.
And, if you're capable, maybe consider supporting them on Patreon. It really does help keep this kind of high-quality educational content coming.
And a big shout out to all their existing supporters. You guys help us a lot in creating this kind of content.
We really appreciate it. And just a quick note from them, don't forget to like their video, share your comments.
Oh, and the Telegram channel. They have a Telegram channel where you can get free notes and practice PYQs.
That's amazing. And for the really serious learners, there's a private Telegram library.
Right, with premium notes, model mains answers.
Yeah.
Everything's organized perfectly. You just DM their public channel to join that.
Okay, we'll remind you about all those links at the end. But for now, let's get back to this continental car crash.
Let's.
What I love about this topic is that it answers the so what question so quickly. You might look at a map and just see a list of mountains or rivers to memorize. But understanding the structure, the geology underneath.
It explains everything else. It really does. It explains why we find coal in some places and gold in others. It explains why landslides happen constantly in the Himalayas, but are, a different beast entirely in the Western Ghats.
It even explains why some ports are great for parking massive ships and others are just terrible for it.
It's the hardware that runs the software of our daily lives.
That's a perfect way to put it. So let's start with the origin story. Section 1, the Great Migration. I think most people have this vague idea that the continents used to be connected, right? Like Pangaea.
Yes, that's the starting point. But the specifics of India's journey are, frankly, wild. We have to look at the geological evidence. If we go back about 140 million years,
Okay.
India wasn't in the northern hemisphere at all. It was sitting way down south, around 50 degrees south latitude.
50 degrees south? Wait, that's nowhere near where we are now. That's almost Antarctica territory.
It is. India was a large island just sitting off the coast of Australia, and it was separated from the Asian continent by this vast body of water called the Tethys Sea.
So it was part of that supercontinent, Gondwanaland.
Exactly. We were neighbors with Australia and Antarctica.
It's so hard to imagine India being that cold.
Well, the climate was different then, of course, but yes, the location was radically different. Then the breakup happens. Around 200 million years ago, Pangaea broke apart, and eventually India snapped off from Gondwanaland and started this long, long northward drift.
Like a giant raft.
Think of it as a massive raft of rock just floating on the semi-molten mantle beneath it, and it moved pretty quickly, geologically speaking.
When you say quickly, what are we talking? Are we talking race car speeds?
For a continent, yes, it was sprinting. And as it moved north, that Tethys Sea we mentioned.
Yeah, the sea between India and Asia.
Right. Its floor was accumulating sediments for millions of years. Dead sea creatures, sand, silt, you name it, just layers upon layers of gunk.
And then?
Impact. Yes, the collision. It happened with the Eurasian plate roughly 40 to 50 million years ago. And this is the key to understanding the Himalayas. This is what we call continent convergence.
Okay, let's unpack that term. Convergence, I get it, means crashing. But why does continent matter so much?
It's all about density. Usually when an ocean plate hits a continental plate, the ocean plate is heavier, it's denser, so it slides underneath. That's a process called subduction.
Right, it sinks back into the mantle.
But here you have India and Eurasia. Both are made of buoyant continental crust. They're both floaters.
So it's an unstoppable force meeting an immovable object.
Exactly. Neither one wants to sink. So all that immense pressure has nowhere to go but up.
Oh.
The crust folded, it faulted, it was thrust upwards. And remember all those sediments sitting on the floor of the Tethys Sea?
All that gunk.
All that gunk got squeezed, compressed, and lifted thousands of meters into the sky to form the mighty Himalayas.
That's why you can find marine fossils at the top of Mount Everest.
That's exactly why.
The highest point on Earth used to be the ocean floor.
It creates a sense of vertigo just thinking about it. But wait, before we fully formed the Himalayas, there was a fiery pit stop during this journey north.
The Deccan Traps. This sounds like an adventure movie title.
It was certainly dramatic as the Indian plate was racing north somewhere around 60 million years ago. So this is before the main collision with Asia was fully complete.
Okay.
It passed over a geologic hotspot, specifically the Reunion hotspot.
A hotspot, is that like a blowtorch in the mantle?
That is a perfect analogy. Think of a blowtorch that's stationary, deep in the mantle. The plate is moving over it like a conveyor belt. And as India passed over this blowtorch, it just punched a hole right through the crust.
And I'm assuming it wasn't a small pop.
It was a massive volcanic outpouring. We call these flood basalt provinces. It wasn't just a single volcano erupting like Mount Fuji. It was highly fluid lava just flooding out through fissures in the ground, covering hundreds of thousands of square kilometers. This formed the Deccan Traps.
I've always wondered about the name traps. It sounds like a snare or something.
It actually comes from the Swedish word trappa, which means stairs. Because the lava flowed out in layers and then cooled, when you look at the landscape today, it has this step-like terraced appearance, like giant stairs. This covers most of the Maharashtra Plateau today.
And looking at the source material, this is a prime example of that idea. Geology is destiny. Because this event, 60 million years ago, basically dictates the economy of that region today.
Precisely. That basalt rock is rich in iron and magnesium. Over millions of years, it weathered down to form regur soil, or as it's more commonly known, black cotton soil.
Because it holds moisture incredibly well.
Incredibly well. So you get a volcano 60 million years ago, and you get a booming cotton industry in Maharashtra today.
That's the connection.
And one interesting little detail from the source text mentions dikes. In western Maharashtra, you often see these weird wall-like structures standing perpendicular to the ground.
They look man-made, right? Like ancient fortress walls?
They do, but they're purely geological. Those are dikes. It's magma that tried to push up through vertical cracks in the ground, but cooled and solidified inside the earth.
So it formed a vertical wall of hard rock underground.
Yes. And then, over millions of years, the softer rock all around it eroded away, leaving that hard rock dike standing there exposed.
So we have this ancient wandering plate that gets sunburned by a volcano and then smashes into Asia. This violence gives us the three main geologic divisions of India. The NCERT book lists them out.
Correct. The Peninsular block, the Himalayas, and the Indo-Gangetic plain. And it really helps to think of them as characters with very, very different personalities and ages.
Okay, let's typecast them. The Peninsular block. This is the south.
Yes. This is the Old Guard. It's the original part of the plate that broke away from Gondwanaland. It's made of ancient gneiss and granite, some of the oldest rocks on the planet.
So it's tough.
It's very rigid and stable. It hasn't been submerged under the ocean much in its recent history, so it's standing firm.
Oh.
It's basically a solid block of resistance against all this tectonic action.
Okay, character 2. The Himalayas.
The young and restless.
I like that.
They're what we call young fold mountains. They are flexible, they're weak, and they're made of sedimentary rocks that were folded up from the sea. And because they're still rising...
Right, the collision isn't over. India is still pushing north.
Exactly, so they're tectonically unstable. This is why we have so many earthquakes in that region.
And the third one, the Indo-Gangetic plain.
That's the filler.
The filler. That sounds a bit derogatory.
Not in its function, but in its origin. Think about it. When the Himalayas rose up in the north and the peninsular block stayed put in the south, what did you get in between them?
A huge gap, a ditch.
A massive depression, a
Mhm.
trough, a giant continental-sized ditch.
And nature abhors a vacuum.
Exactly. Over millions of years, the rivers flowing down from the new mountains and up from the old plateau filled this depression with sediment. Silt, sand, clay. Layer after layer after layer. That's the Indo-Gangetic plain.
Which makes it incredibly fertile. Okay, so we have the sable block, the unstable mountains, and the filled pit. I want to zoom in on how this difference in personality plays out in real life. There was a mains question from the UPSC exam in our notes that asked specifically about landslides.
Yes, this is a classic application question. It's a great one. It asked, why do landslides occur frequently in the Himalayas, but less frequently in the Western Ghats or Nilgiris?
And on the surface, you might think, well, they're both mountains, they both have steep slopes, they both get a lot of rain. Why the big difference?
And it comes down to that internal stability we just discussed.
Mhm.
The Himalayas are tectonically active. The rocks themselves are sedimentary and unconsolidated, which is a fancy way of saying they are loose and fractured.
So they're not solid.
Not at all. The mountain itself is physically crumbling from the inside because of the immense tectonic stress. It's weak.
So in the Himalayas, the mountain's own structure is the villain.
In a way, yes. But then you look at the Western Ghats. They are part of that peninsular block. They are tectonically stable. They're made of very hard, ancient rocks. Landslides do happen there, but the cause is different.
How so?
In the Western Ghats, landslides are usually triggered by external factors.
Like rain.
Exactly. Heavy rainfall on steep vertical cliffs or mechanical weathering from temperature changes. It's not because the mountain is tectonically buckling. It's because gravity and water are acting on the surface debris, the soil, the loose rocks on top.
That is a crucial distinction. Internal crumbling versus external washing away. It really highlights why building anything,
Right.
roads, dams,
Mhm.
in the Himalayas is so much more difficult.
Absolutely. You are fighting the earth itself.
Let's keep moving north and really decode the Himalayas. I used to think of the Himalayas as just one big wall of snow, but the sources break it down into parallel ranges.
It's definitely not a single wall. You have to think of it as a series of ranges running parallel to each other. Furthest north, you have the Great Himalayas, the Himadri. That's where you find the big peaks like Everest and Kanchenjunga.
The big ones.
Then south of that, you have the Lesser Himalayas, or the Himachal, and finally the Outer Himalayas, also known as the Shiwaliks, which face the plains.
And the text gets really specific about the regional quirks.
Yeah.
Let's talk about Kashmir. The source material spends some time on a term called Karewas.
Ah, yes, Karewas are fascinating. To understand them, you have to imagine a time during the Pleistocene epoch when the Kashmir Valley wasn't a valley of flowers, but a massive lake.
A giant lake trapped in the mountains.
A huge one. And the rivers and glaciers flowing into this lake dump thick layers of clay, sand, and silt, layer upon layer. Eventually, the water drained away, leaving these elevated tablelands of deposits. These are the Karewas.
And why do we care about old lake mud?
Because of saffron. The famous saffron of Kashmir grows best in these Karewa formations. It's a perfect example of geology dictating agriculture. You can't just grow that specific saffron anywhere. You need that specific glacial lacustrine soil structure.
Lacustrine meaning lake-related.
Correct. Old lake bed.
Okay, moving east from there, there's a mention of duns, like Dehradun. I visited Dehradun, it's beautiful. But what is a dun, geologically speaking?
A dun is a longitudinal valley. As the mountains were folding and rising, long troughs formed between the Lesser Himalayas and the Shiwaliks.
So valleys that run parallel to the mountain ranges, not cutting through them.
Exactly. And these troughs then got filled with gravel and alluvium washed down from the higher ranges. So Dehradun, Kotli Dun, Patli Dun, these are all structural valleys. They're essentially flat floors nestled between the rising ranges, which made them great places for people to settle.
Now, here's a weird one I noticed in the notes. The text says the Shiwaliks, that outer lowest range, are missing in the east, like around Darjeeling and Sikkim.
That's a sharp observation. And it's true, in the western part of the Himalayas, the Shiwaliks are broad and very distinct. But as you go east, the Himalayan ranges get squeezed together. The whole mountain chain curves, creating this intense compression.
So they just kind of merge?
In the Darjeeling and Sikkim sector, the Shiwalik formation is almost absent, or it's very, very narrow. The plains essentially ram right up against the steeper mountains. There's no gentle foothills zone.
And this actually links to a question about tea gardens.
Mm-hmm.
Why did the British have so much success with tea in Darjeeling and Assam, but not necessarily everywhere in the Himalayas.
Tea is a very fussy plant. It requires a really specific set of conditions. It needs moderate slope so water doesn't stagnate. Waterlogging will kill the roots, but the soil must also be deep and acidic.
So it needs a lot of rain, but it needs the rain to leave immediately.
Exactly, you've nailed it. The Darjeeling Himalayas offer exactly that. Steep slopes for excellent drainage, very heavy rainfall, but also excellent soil depth. In the Shiwaliks further west, or on the flat plains, the conditions just don't match up in the same way.
Interesting.
While we're in the Northeast, let's talk about the rivers. The Brahmaputra system is massive. And there was a specific prelims question that asked which rivers are tributaries of the Brahmaputra. The options were Dibang, Kameng, and Lohit.
Okay.
And the answer is all three. The Brahmaputra is a beast of a river. It flows through Tibet as the Yarlung Tsangpo, originating from the Shemo-Yungdong Glacier.
That's a mouthful.
It is. Then it enters India in Arunachal Pradesh as the Shang. And then two major tributaries, the Dibang and the Lohit, join it from the left. That's when it officially becomes the Brahmaputra in Assam.
And a Kameng.
The Kameng comes in from the right bank a bit later on.
It's a good reminder that physiography isn't just about the mountains, it's the plumbing system of the continent, too. Knowing which pipe connects to which is crucial for understanding floods, water resources, everything.
Speaking of plumbing, let's head south to the Peninsular Plateau. This is that inverted triangle that makes up the bulk of southern and central India.
The Old Guard, the stable block.
Yes. But even the Old Guard has some mysteries. The general slope of the Indian Plateau is from west to east.
Okay, how do we know that?
We know this because almost all the major rivers, the Mahanadi, the Godavari, the Krishna, the Kaveri, they all start in or near the Western Ghats and flow east across the entire country to dump into the Bay of Bengal.
Right. Gravity 101. Water flows downhill.
Okay.
But there were two rebels, the Narmada and the Tapi. They flow west. Why? Did they not get the memo about the slope?
This is a favorite question for geographers and for the UPSC. It forces you to look beyond the surface slope. The Narmada and Tapi aren't flowing down a simple hill. They're flowing inside a rift valley.
A rift valley. Okay, break that down for us.
Remember we said the peninsular block is rigid? Sometimes, under stress, rigid things don't bend, they crack.
Right.
So parallel faults cracks developed in the crust, and the block of land between them sank down. That sunken trough is a rift valley.
So it's like a crack in a sidewalk, but on a continental scale.
A crack that is hundreds of kilometers long. The Narmada flows between the Vindhya Range to its north and the Satpura Range to its south. It's trapped in this linear trough, so it doesn't matter what the general slope of the wider plateau is, the river has to follow the path of the fault line.
So it's like a gutter running across a sloping roof.
Yeah.
Even if the roof slopes one way, if the gutter runs the other way, the water follows the gutter.
That is a surprisingly accurate analogy.
Yeah.
Yes. And because they flow through these hard rock rift valleys, they don't carry as much sediment as the Himalayan rivers.
And what's the implication of that?
Well, here's the kicker. Because they dump into the deep Arabian Sea coast through these rocky channels, they don't form extensive deltas like the eastern rivers. They form estuaries.
Okay, comparing the rivers of the south to the rivers of the north is another major theme in the source text. They call the Himalayan rivers youthful and the peninsular rivers mature or even old. What does that mean for a river? Does it have a midlife crisis?
In geomorphology, age is all about the shape of the valley and the energy of the flow. A youthful river, like the Ganga in the upper Himalayas, is aggressive. It has a steep gradient, it flows fast, and its main job is to cut downwards. It carves deep, V-shaped valleys and gorges.
So it's energetic and destructive, carving up the landscape.
Exactly. It's still actively shaping the landscape, trying to reach what we call base level. But the peninsular rivers, the Godavari, the Krishna, are mature. They've been flowing over that stable block for millions and millions of years.
They've already done the hard work.
They've already eroded their valleys down. Their valleys are broad and shallow. The gradient is gentle. They aren't cutting down anymore. They're mostly just carrying water and shifting side to side.
They've settled into a comfortable retirement.
Essentially. They flow through what geographers call peneplains, which means almost plains, with these random little resistant hills called monadnocks sticking out here and there.
I love the word monadnock. It sounds like a sci-fi villain. Beware the monadnock.
It's actually a term from a mountain in New Hampshire, but we use it in Indian geography to describe those lonely, hard rock hills that are left standing after the surrounding plain has been completely eroded away.
Let's move to the edges.
Ah.
The coasts. India has a massive coastline, but the West Coast and the East Coast are totally different experiences.
Oh, night and day. The West Coast, think Mumbai, Mangalore, Kerala, is largely what we call a submerged coast.
Submerged, like Atlantis.
Not that dramatic. But geologically, the western margin of India faulted and subsided a bit. It sank. This means the sea comes right up against the land, creating a steep, rocky coast in many places. The land drops off quickly into the sea.
Which means the water is deep, close to the shore.
Exactly, and that is great for ships.
Perfect for natural harbors.
Absolutely. That's why you have major natural ports like Mumbai, Marmagao, and Cochin on the west. You don't need to dredge massive channels because the water is naturally deep. It also creates those beautiful creeks and estuaries.
Okay, so what about the East Coast?
The East Coast, think Chennai, Vizag, Odisha, is an emergent coast. It's a low sedimentary coast. The continental shelf extends far out into the sea. Plus, all those big east-flowing rivers we mentioned are dumping tons and tons of silt there.
Building up land.
Yes, building massive deltas. So the water is very shallow for a long way out.
Which is terrible for ports.
Exactly. Ships can't get close to the shore. You have to dredge massive channels or build entirely artificial harbors like the one at Chennai just to get big ships in. So historically, the West Coast was naturally much better suited for maritime trade, at least in terms of accessibility.
That brings us to the islands. We've got the Andaman, Nicobar Islands in the Bay of Bengal and Lakshadweep in the Arabian Sea. Are they just peaks of submerged mountains?
Andaman and Nicobar largely are, yes. They are essentially a southward extension of the Arakan-Yoma mountain range in Myanmar. They're the peaks of elevated submarine mountains.
Okay.
And some of them are even volcanic. Barren Island in the Andamans is India's only active volcano.
A volcano in India. I thought we were done with those after the Deccan Traps.
Barren Island is still very much alive. It last erupted quite recently in geological terms. It's a good reminder that these tectonic forces are still very active. But Lakshadweep is a completely different story. They aren't mountains at all.
What are they then?
They're coral deposits.
Atolls?
Yes. They are built on submarine platforms by tiny coral polyps over thousands of years. So Andaman is rock and volcano. Lakshadweep is coral and calcium carbonate.
Speaking of coral, there was a tricky prelims question about where coral reefs are found in India. The options were Gulf of Kach, Gulf of Mannar, Andaman and Nicobar, and the Sundarbans.
And this is where you have to know your environment, not just your geography. Corals are very picky. They need clear, warm, saline water to survive.
Right.
Now think about the Sundarbans. It's a massive delta. The water there is fresh to brackish because of the huge river outflow from the Ganga and Brahmaputra. But more importantly, it is incredibly muddy and silty.
Visibility is basically zero.
Exactly. Sunlight can't penetrate that silt. And corals need sunlight for the algae that live inside them to photosynthesize. So in that muddy, silty water, corals would just suffocate and die.
So the Sundarbans do not have coral reefs.
Absolutely not. The answer to that question excluded them. It's logic, not just memorization. Mud kills coral. Got it.
Got it. We should also touch on Section 6 from the outline. Process and evolution. The notes mention geomorphology. This connects to the fundamentals textbook. We've talked about the structure, but the process is what shapes that structure, right?
Yes. The tools that carve the rock, the two big ones are glaciers and rivers.
Glaciers are like bulldozers.
That's a great way to put it. In the Himalayas, they carve those classic U-shaped valleys, and as they move, they push and drag enormous piles of debris, which they leave behind as moraines. The Karewas, we mentioned in Kashmir, are partly glacial fluvial deposits.
And rivers are more like artists.
Rivers are more like sculptors. They create V-shaped valleys when they're young and energetic, but when they hit the flat plains, they get lazy and start to snake around. They form meanders.
There's a great satellite image mentioned in the source material of the Burhi-Gandak River. It shows these crazy loops and these little crescent-shaped lakes. What's happening there?
That image is a perfect lesson in fluvial geomorphology. A river on a flat plain naturally wants to take the path of least resistance. So it bends. The water moves faster on the outside of the bend, which erodes the bank.
And it moves slower on the inside of the bend.
Exactly, which causes it to deposit sand and silt, forming what we call point bars. So the curve gets more and more exaggerated over time. It creates a big loop.
Okay.
Eventually, the loop almost touches itself. The neck of land gets very narrow. Then, during a flood, the river just breaks through that narrow neck and takes the shorter, straight path again.
And the old loop is left behind.
It's cut off from the main channel and becomes a stagnant, crescent-shaped lake, an oxbow lake.
Nature straightening itself out.
It's a dynamic process. The plains of North India are just full of these scars of old river paths. It shows us that the land is alive. It's constantly changing.
This brings us to the end of our journey across the Indian plate. We've gone from the breakup of Gondwanaland to the volcanic Deccan Traps, the buckling Himalayas, the rift valleys of the south, and the shifting rivers of the plains.
And the key takeaway for me is the connectedness of it all. You can't understand the agriculture of Maharashtra without understanding that volcano 60 million years ago.
Right.
You can't understand the landslides in Uttarakhand without understanding the plate collision.
And you can't understand why we can't park a big ship easily in Odisha without knowing it's an emergent coast.
Exactly. The structure, the rock underneath, determines the physiography, the surface we see, and that physiography determines how we live.
Before we wrap up, I want to leave our listeners with a thought that was in the source material. We talk about the collision like it's a historical event. India collided with Asia, past tense.
But it's not past tense, it's present continuous. The Indian plate is still moving north at about 5 centimeters per year.
Which is roughly the speed your fingernails grow.
Yes, which sounds slow, but for a continent, that's sprinting.
It is.
The Himalayas are still rising, the stress is still building up in the rocks. We are living in a freeze frame of a slow-motion car crash that isn't over yet.
So in a million years, the map of India isn't going to look like this. The Himalayas might be wider. The Indo-Gangetic plain might be squeezed even smaller. We're just temporary tenants on a moving raft.
A very humbling thought.
Truly. Well, that's our deep dive for today. A huge thank you again to the Simplified UPSC by PPP channel for the incredible source material connecting the textbook to the actual exams.
Please do subscribe to their channel, check out their Patreon if you want to support this amazing work, and join the Telegram channel for all the notes and PYQs we discussed today. The links are usually in their descriptions.
And for the serious aspirants, don't forget that private library on Telegram for the premium notes and the model answers.
It's a fantastic resource.
Thank you to you, the listener, for joining us on this geological road trip. Keep asking questions, keep looking at the landscape around you a little differently, and we'll catch you on the next deep dive.